assuming that the particles are size, and they wait when they collide, they cannot be closer. They cannot overlap. There is a minimal distance they can reach. Now, from these, and after a certain number of assumptions, we at the end derive the equation of state of real gas, the van der Waals equation of state, that had these features. In particular, when plotting the isothermal lines, we saw that some new features appear with respect to the case of ideal gas, which were the following. Let's say the equation of state looks like the standard one for T larger than the critical temperature. Then we have the T equal Tc equation of state curve. This is P and this is V volume. And there was after that this weird behavior at T smaller than Tc. And now this behavior here, we said that was a kind of empirical, phenomenological description of first order phase transition. Okay. Indeed, let's talk about this a little bit more. So the case T less than Tc, and we were saying that once we have the PV diagram, there were 2 points. I don't remember now the name we gave, A and B, in which the system is unstable with respect to mechanical perturbations, because the isothermal compressibility is negative. And indeed, we somehow cured this problem of the van der Waals gas by considering what is called a Maxwell construction. The Maxwell construction, once we do it, Maxwell construction, somehow it's a way to go beyond this instability and to look at the system, to consider the system once it is in mechanical equilibrium or in thermodynamical equilibrium more generally. And indeed, when doing that, what we discover is that we have a situation like that. So this pressure here, for which the area S1 and S2 are equal, corresponds to the equilibrium pressure of the two phases in coexistence. Okay? So this is the plateau, the pressure corresponds to the mixed phase. Mixed phase, which means two phases with same pressure and same temperature. Which is exactly the behavior that we see empirically when we have to deal with the first order phase transition, like a liquid gas phase transition or the melting of ice. Okay, we see a plateau in the pressure. This diagram here was also connected, but actually this is the derivative on another diagram, which was the following. Let me remove this. The diagram of A, so the Helmholtz free energy, as a function of the volume, and we say this something like that, where the 2 points corresponding to the mixed phase are those points here. So here should be tangent. So this is again a Maxwell construction. But in the diagram A versus B. Again, here the temperature is fixed. And we see that this phase here corresponds exactly to the mixed phase, because this line here has a derivative which is constant, that in that diagram there corresponds exactly to a plateau in the pressure. Okay? And this mixed phase, you see, has a smaller Helmholtz free energy with respect to the Helmholtz free energy predicted by the van der Waals equation of state, and therefore, for the second principle of thermodynamics, the system will like to separate into phases, which form this mixed phase. Okay, and here the equation of state of A, let's say that the function, the Helmholtz free energy, is a sort of average of the Helmholtz free energy of the two phases, something like that, because it's a line, a straight line, where chi is the fraction of one of the phases, or phase 1, and 1 minus chi is phase 2. Okay, so here what would we summarize? We introduce a small correction to the interaction, or introduce a sort of interaction of particles, and we get something which is very rich for what concerns the phase diagram. Okay, we have somehow found a behavior which is the one of the mixed phase, etc. Okay, so this situation describes actually in an accurate way the liquid line phase and the liquid gas phase transition. For water, it was something like that. This is liquid, and this is gas. Okay, so we are talking about this line here, which is a first order phase transition, first order transition line. What to do else for this potential, for this prediction of the van der Waals gas? Just let me say a few words more, and then we go on and we will study a little bit more in detail the mixed phase. The Maxwell construction describes the situation at the thermodynamical equilibrium, which means that the system has say, enough time to sit into the thermodynamical equilibrium state. Actually, from experience, you know that there are some phenomena like supercooling or supersaturated gas, which are somehow also considered in this kind of construction, and that corresponds exactly to this point here that I'm going to describe. So this was the equation of state of the real gas. This is the unstable branch, and this is the pressure of equilibrium. Now, what happens is that at the equilibrium, you will have a plateau here in the pressure. Actually, when you try to cool down vapor or to boil liquid into its vapor, you do not see immediately the formation of a mixed phase, which is then in thermodynamical equilibrium, but you have some sort of formation of metastable states, which are exactly forming here. So in this region here, and in this region here, you have metastable states. And again, similarly for this case. What are these metastable states? It could be that when you compress the liquid in order to, when you compress the gas in order to obtain a liquid in an isothermal, it could be that some bubbles of vapor are still there, even if you have reached the first order phase transition line. Let me be more clear. So suppose that we are in this situation, this critical point, this threshold point, and you have a gas here, vapor, is liquid. Suppose that you are compressing this pressure, this is temperature, that you are compressing the gas at a fixed value of the temperature. Now, at equilibrium, in this point here, you will start to form the mixed phase. But actually, what happens in reality is that you go beyond a little bit, so you still stay in the gas, which is supersaturated gas, and then after that you will form the liquid. Okay. This trick, for instance, is using in some particle detectors. No, when you have a supersaturated gas and the particle passing to the box, and then you have a condensation, right? Maybe you have studied this some lab exam. So these are phenomena of supercooling, for instance, or supersaturated gas. These are all processes which are out of the thermodynamical equilibrium and are, for instance, called nucleation, of, say, the new phase into the old phase. Or there are some other processes which are, so the nucleation proceeds like the term, like the word is saying, by nucleating, so forming some droplets of the new phase inside the old phase. Or another phenomenon that could happen is the spinal decomposition, which occurs between B and A. So up to this point here, to the maximum, you have the metastable states formed in the regime of nucleation, whereas here in the unstable branch, you will have another phenomenon which is called spinal decomposition, which is a sort of very fast clusterization of the new phase inside the old phase. Okay. So this kind of physics is beyond the thermodynamical description, and it's let's say falls into the regime of non-equilibrium statistical mechanics that we will not treat in this course. But I mean, it is anyway good to know these names, which are nucleation and spinal decomposition, what they are. Okay, so they are the processes which are somehow non-equilibrium processes that are occurring when you have the conversion, well, when you have a first order phase transition before you reach the thermodynamical equilibrium. Okay, so this is to say that again, this van der Waals gas contains really a lot of physics, and also you have the possibility to describe also in principle non-equilibrium processes like those ones. And I think for this part is enough. Now we will study a little bit more in detail the mixed phase. We will introduce a quantity which is the latent heat, which characterizes the first order phase transition. And at the end of this day, probably we'll do the Gibbs rule for the phases, and that's it. Okay, so let's concentrate for a moment, well, for the rest of this lecture, on the liquid gas phase transition. So we are basically here. So here, with that trouble point, so but this is the liquid and this is the gas. Now we said that, and so let's talk about the mixed phase now. The mixed phase that is occurring along this line here You can change the pressure and the temperature depending on the temperature and different pressure of equilibrium of the two phases, which is the vapor pressure. The mixed phase is composed by two phases, which have the same pressure, same temperature, because you are sitting exactly on one of these points here of the belonging to the first order phase transition line. And now we will see that actually they also have the same chemical potential as it should be in thermodynamical equilibrium. Indeed, remember that we have the Gibbs potential that was defined as well, G is equal to A plus PV, and we say that this is equal to mu times N, where mu is the chemical potential, and N is the number of particles. Now, suppose that we have a phase 1. Let's consider phase 1 to be the liquid, and phase 2 to be the vapor or the gas. Okay. And now those two phases are in mechanical and thermal equilibrium in the sense that they have the same pressure and the same temperature. Now, if you change somehow the amount of liquid, or equally saying the amount of gas, a total fixed number of particles, what will have to the Gibbs potential? The Gibbs potential will change also, no? So suppose that you now change the number of particles of phase 1 by an amount which is delta N1, for instance. Of course, by conservation of number of particles, delta N, sorry, this is 1, of course, delta N1, you should have an amount of change of phase 2, which is such that delta N1 plus delta N2 is equal to 0. No? I think we have done this exercise another time. So delta N2, it must be equal to delta N1. Okay. So what we are doing here is to somehow study the equilibrium of the mixed phase with respect to the change of the number of particles in one phase and in the other phase. Now, the second principle of thermodynamics tells me that once you have fixed pressure and fixed temperature, then the potential that you have to minimize is the Gibbs potential. Okay, so at fixed P and fixed P and fixed T, you have to minimize Gibbs. And at equilibrium, that means also that the variation of the Gibbs potential must be 0, because there is no other way to make smaller the Gibbs potential. So that means that the total variation of the Gibbs potential must be 0. This is for the second principle. And now this delta G is delta G1 plus delta G2, and delta G1 and delta G2 are mu1 delta N1 plus mu2 delta N2. And now, since delta N1 and delta N2 are one of the opposite of the other, so by using this equation, that implies that mu1 is equal to mu2. So the two phases are not only in pressure and mechanical and thermal equilibrium, but they are also in chemical equilibrium. Okay, this is chemical equilibrium. Okay, so the two phases have the same pressure, the same temperature, and the same chemical potential in the mixed phase, in order to be at the thermodynamical equilibrium, which means minimize the Gibbs free energy. Okay. Now, once we have derived this result, we can look at another diagram. Instead of PV or PT, we can describe the phase transition now in another class of diagram, in which we also introduce the chemical potential. So let me write again G is equal to mu times N, from which we derive that mu is equal to mu is G divided by N, which is, if you want, the Gibbs potential per particle. This is another, if you want, interpretation of the chemical potential. This is the Gibbs potential per particle. And now let's make a plot of mu as a function of P and T by reminding that from the second law, one has to minimize G. And that means that in the mixed phase, you have the two phases are separated, but they are in chemical, mechanical, and thermal equilibrium. In the pure phase, so pure phases, for pure phases, the phase with smaller mu, let's say, wins. By wins, I mean it will substitute the other one. Let me be more clear. Now, we have a diagram here that we can make now, in which we involve also the chemical potential, the pressure, and the temperature. So this is mu, and this is T. And for a single phase, in general, mu is a function of pressure and temperature. We also derived an equation for that, in which we have a relation between pressure, temperature, and chemical potential. And the situation will look like the following. So P constant, so fixed value of the pressure. You will have something like that. Let me make the plot in a reasonable way. So suppose that the dashed line corresponds to phase 1 and the continuous line to phase 2. Now, in general, those two phases are different, of course, and therefore the behavior of the chemical potential as a function of pressure and temperature will be different. Okay, that's why here I'm drawing different lines, because they are different phases. But for this point here, which corresponds exactly to the mixed phase, because at this point you have the same pressure which is this one, is fixed, same temperature and same chemical potential. So in this diagram, it's very easy to find the phase transition because it's just the intersection of the chemical potential lines. Okay, so this is the mixed phase, and let's make a similar plot in which instead of temperature we have the pressure, and it looks like that. Of course, one could ask himself what determines the slope of those lines. This can be done by computing the equation of state of van der Waals, by deriving the chemical potential, and you will see that the slope is like that. So now here we have, instead of mu as a function of t, we have mu as a function of t, at t constant. And the situation will be like that. Allora, la 1 l'ho disegnato dashed, quindi facciamola così. This is phase 1, and this is phase 2, where 1 was liquid and 2 was gas. I remember correctly what we did before. And again, in this plot, the point at which mu and p are equal for the two phases is the mixed phase. Now, this, let's say, the results that you have when comparing the chemical potential of the two phases as a function of T and pressure, fixed temperature and pressure. But now we know, for what I'm writing here, that the second law establishes that at fixed pressure and temperature, I have to minimize the Gibbs free energy, which means minimize the chemical potential, basically, once the number of particles is fixed. Therefore, what we did before for the Helmholtz free energy, now we can do it similarly here and say that at equilibrium, let's make it, let's make a line here. Now, here, that means that when I have an equilibrium state, which is the one that we can describe in thermodynamics, actually the plot will be the following. I have mu, T, fixed pressure, and here what wins? It wins the phase with the smaller chemical potential. Okay? So then in here I will have phase 1, whereas in here I will have phase 2. So the plot actually of the equilibrium state will be something like that. Okay, so this is the mixed phase, this is phase 1, this is phase 2. And I can remove the other lines because they are just corresponding to a metastable phase. Okay. And similarly, for the other plot, here we have mu as a function of pressure at fixed temperature. And again, which is the phase that wins, is the one with the smaller chemical potential at fixed pressure and temperature. And therefore, we'll have something like that. Now, this is 2, and this is 1, this is 2. Yeah, 2. And this is 1. Okay. This describes the behavior of the two phases separately and the mixed phase, but we know from the second law that the phase with the smaller Gibbs potential wins, therefore the equilibrium will be like this. Okay? So this is again the phase diagram, but in another region, in another plot, in the mu T plot, in which you can see that you can distinguish among the different phases by just looking at the chemical potential. And now this provides also the explanation for which this kind of transition are called first order phase transition. Why first order? You see here that if you consider mu as a function of t and p, you see that there are this discontinuity. So at the transition point here, you see that at the transition point, you see here that there are derivatives which are discontinuous. So the derivative of mu1 with respect to T1 at fixed pressure is different from the derivative of mu2 with respect to T2 at fixed pressure, mu1, T1, and similarly for this case, the derivative of mu1 with respect to P1 at fixed temperature is different from the derivative of mu2 with respect to P2 at the same temperature. Okay. Now, the fact that they are called first order phase transition is exactly the following. So you have a function which is mu, which is continuous as a function of t and p, but it has discontinuities in the first derivative. Okay, so first order means discontinuity in the first derivative of the chemical potential. So this means first derivative, derivatives are of the chemical potentials of mu, which is a function of p and t, are jumping. Okay. So this classification of phase transition is the one which is mostly followed. So you have a first order when you have a discontinuity of the first derivative of mu, second order when you have a discontinuity of the second derivative of mu, etc. Third order, and so on and so forth. Actually, the distinction between the phase transition is actually done in the following way. You have first order, second order, which correspond to the critical point that we will see, and then you have what is called crossover. Okay? Third order phase transition are not usually taken into account, they are just called crossover, so which is a very smooth transition. First order instead is not smooth at all, because you have this discontinuity, and you will have some features that now I'm going to describe that are the jumps in the density of the two phases, and the latent heat, which is also another quantity that characterizes first order phase transition. Now, let us remember that dg, it was equal to minus s dt, and then we have a plus b dp, where I am imposing dn equal to 0, conservation number of particles in the single phase, from which I derive that the derivative of g. Well, let us divide this by n. Let us divide this by n. I think it's the mostly is the best way to do it. Let's divide this by n, and n. there is something wrong here. This, of course, is just the PDP. Now, this the variation of the chemical potential per particle, or the variation, sorry, of the Gibbs potential per particle, which is just the variation of the chemical potential. So from this, I derived the derivative, the partial derivative of mu with respect to temperature at fixed pressure is equal to minus S, which is entropy density. Sorry, is entropy per particle. S divided by N is small s. I define this quantity, and there is a minus. Okay? So d mu dt at fixed pressure is minus the entropy per particle, and also from this equation, I derive that d mu with respect to pressure at fixed temperature is 1 divided by the density, so it's 1 over n, where n is the density of particles. It is equal to n divided by u by the density of particles. Okay. So I see that these two derivatives are minus s and minus n, and for what I said before, those derivatives are jumping at the transition point for what we said in first order phase transition. Okay, they are different because the slopes were different, so that means also that in the mixed phase, while pressure, temperature, and chemical potential are equal of the two phases, the entropy per particle of phase 1 is different from the entropy per particle of phase 2, and the density of phase 1 is different from the density of phase 2. Okay? So at the end of the day, you will have two phases in thermal, mechanical, chemical equilibrium, but having different entropy per particle and different density, which is exactly what we see in reality when we have a mixture of ice and water, for instance, of a mixture of vapor and liquid. Okay, so they have different density, but they also have actually different entropy. Okay. And indeed, let us introduce now a quantity which is which characterizes even more first order phase transition, which is called the latent heat. The latent heat is basically just this difference of entropy per particle that we derived before. So let us introduce a quantity which is called the latent heat. What is this latent heat? So let's consider again the Gibbs potential. G is equal to this A plus PV, which is also U minus TS plus PV, and divide by N. This is the chemical potential now. This is let's call it E, so energy per particle. This is minus T times small s, which was the entropy per particle, plus P, and here I have divided by M, which is the density. Now, we said before, but we look at it in a different way. The delta G divided by M must be equal to 0 in the mixed phase, because we are in equilibrium. So that means that if I do it from here and consider phase 1 and phase 2, I have the difference between P1 minus Ts1 plus P divided by N1 minus P2 minus Ts2 plus P divided by N2 must be equal to 0. From which I can derive the following. Let me see if it is correct. Minus S2, P divided by N2. Okay. From which I can derive the following equation. I have a T times S2 minus S1, which is equal to the pressure, we put it in the other side. There's a minus there, so it becomes a plus 1 divided by N2. 1 divided by N2. 1 divided by N2 minus 1 divided by N1. And then I get the difference between the energy per particle, which is A2 plus A2 minus A1. Ts2 minus S1 is equal to pressure. That's that difference, and A2 minus A1. Now, this reminds us the first principle of thermodynamics, because we have a P times delta S. Here I have a P times a difference of volume, and here a sort of difference of internal energy. Now, this quantity here, by definition, is called Q, where Q is the latent heat for per particle. Q is latent heat per particle. Which is equal clearly to T times S2 minus S1 if I want to write it in terms of entropy per particle. Now, of course, this is different. It's different from 0 for what concerns first order phase transition, because we said before that the entropy per particle of the two phases are equal. Okay, so that necessarily there is a finite value of the latent heat per particle. What is this latent heat? You might remember this from chemistry, maybe, or not. I don't know. Are you familiar with the latent heat? No? Yes, or less. Okay. Anyway, this is a quantity that is the heat that you provide to the system, for instance, in a liquid gas phase transition, in order to change, to convert one phase into the other phase. But when releasing this heat, actually, the temperature will stay the same, and the pressure will stay the same, the chemical potential stays the same. Okay, so you provide the heat to the system, but actually the pressure, the temperature, and the chemical potentials are always equal because they are in equilibrium. Okay, so the latent heat. Do you know any application of latent heat in normal life? No? When you go to have a drink, you take a whiskey, you put a lot of ice there, no? And the thing is that if there is a lot of ice, you can decrease the temperature of the ice without melting, no? So that's the idea. Okay? So you somehow use the fact that you have this latent heat. Okay, from this equation, you have from this equation, you can derive what is called the Clapeyron equation, which then allows us to determine also the shape of the first order phase transition line for the liquid gas phase transition. So now what we will do is to divide the so-called Clapeyron. Let me see if I write correctly. Clapeyron Clausius. And suppose again that we are here, so we have pressure, temperature, and we are trying this critical point. We are trying to describe this line here. This liquid, this gas. Now we said that in the mixed phase, the two chemical potential of the two phases are equal, so mu1, which is a function in general, pt, is equal to mu2, which is again a function of tp and t, and p and t are equal in the mixed phase. Two phases are in thermal and mechanical equilibrium. Now, let's try to move, so to make a derivative of this equation by moving along the first order phase transition line. So I write first the derivative and then I will comment on that. Okay. Let's derive this with respect to T, with respect to temperature. So I will have a derivative of mu1 with respect to temperature plus, so the partial derivative, plus the derivative of mu1 with respect to pressure times the derivative of pressure with respect to T. Now we'll comment on that in just a moment. Then I have d mu2 with respect to temperature plus d mu2 with respect to pressure times a derivative of pressure with respect to T. These are derivatives along the first order phase transition line. So I'm moving basically here. I consider a point here and I provide an incremental perturbation temperature. And by moving on this line, I have to consider the fact that the pressure is not independent. So it's not an independent. So it depends on the temperature. That's why here, when deriving this with respect to temperature, I do the derivative of mu1 with respect to temperature, plus using the chain rule, the derivative of mu1 with respect to pressure times derivative of pressure with respect to temperature. Okay. So we are moving along this line because we will determine in a moment the slope of this line, which is the Clapeyron equation. Now it's a matter of just using the previous equation and remember which is with the Maxwell relations in presence of chemical potential. And we see that this equation turns into the following equation. dmu1 with respect to T is minus S1 plus, well, this is 1 divided by N1, this derivative here, derivative of P with respect to temperature, and this is equal to minus S2 similarly, plus 1 divided by N2 derivative of P with respect to T. Okay? Which at the end provides, I can find from this equation the derivative of P with respect to the temperature, which is the slope of the first order phase transition line. No? So the derivative of P with respect to temperature is equal to, let me write the result finally, which is equal to S1 minus S2 divided by 1 divided by 1 minus N2. The following, S1 minus S2. Ok, let me check if this is correct. Cosa ci abbiamo lì? La derivata la portiamo là, 1 diviso N2. Yeah, it should be correct. Okay. Now this is also equal when introducing the latent heat per particle, which was T S2 minus S1. This should be equal to Q divided by temperature, and here should have a 1 minus, considering the minus sign. Okay. Q divided by T, 1 minus temperature. Now this is called Clapeyron Equation. And it provides the slope of the first order phase transition line. Okay. So let's try to see what this equation means. Now this Q is positive, this latent heat is positive, the temperature is positive. This difference could be positive or negative depending on the kind of matter we are talking about and depending on the phases. For instance, let us consider the case of water. So here we have liquid water and here we have vapor. We know that the density, so suppose that phase 1 is water and phase 2 is the vapor. We know that the density of vapor is larger than the density of water. Is smaller. N2 is smaller than N1. If N2 is smaller than 1, dP dt is larger than 0. Okay, from these equations here. So indeed, we see that this line has a positive slope. So it's increasing. The pressure is increasing as a function of temperature along the first order phase transition line. Okay. What happens instead for the case in which, so this is, we said this is vapor, phase 2, and this is water, liquid water. What happens when considering ice and water? Now, for ice and water, it's just the opposite in the sense that water has a density larger than ice. So N2 now, and this is N1, and N2 is larger than N1. If N2 is larger than N1, that means that the derivative of pressure with respect to temperature is negative. And indeed, for water, we have this line with a negative slope. Okay? This ice. So if we change from water to from ice to water, we have that the density of water is larger, and then therefore the derivative of pressure with respect to temperature has a negative slope. Okay? Which is a peculiar fact about water. The fact that the liquid phase is denser than the solid phase is a specific feature of water. This is not general. Indeed, you can find some, what I have here, CO2, anidride carbonica, for which you can have also another slope or other chemical compositions of matter, for instance CO2, you can actually have a phase diagram in which also the solid liquid phase has a positive slope. And you will have something like this. You have a tribal point, then you have a line with this slope here, then you have the first order and the critical point. So for CO2 it's like that. So it's a positive slope. Okay? Now, of course, also the fact that ice and water has, so the fact that you have negative slope, the fact that the density of water is larger than the density of ice has many implications and many applications, right? You know that about the iceberg. Okay, so this is the Clapeyron equation. Now it's 12. Let me maybe find just a final result and then we stop for a moment. Now this is the sign of the slope. We can also determine qualitatively the analytical form of the slope. Well, sorry, not of the slope, but of the first order phase transition line for the liquid gas phase transition. So this is sort of exercise if you want. Suppose that you want to find the analytical form of the liquid gas first order line. So to do that, we need to assume that N2 is much smaller than N1 so that we can neglect it in the Clapeyron-Clausius equation. And two, assume that the gas has the ideal gas equation of state. Okay, so we start with this. dP divided by dt is equal to Q divided by temperature, and here I have 1 is N2 minus N1, which is equal when neglecting N2. Let me see. N2 much smaller than N1. Yeah, of course. N2 much smaller than N1 means that we can neglect N1 for what is done here, no? So the 1 divided by N2 is much larger than 1 divided by N1, no? By assuming this. Therefore, this is nothing but Q times N2 divided by temperature. Okay. And we also know, we also use the fact that PB is equal to KB and T in general, therefore the pressure is equal to KB and T by dividing by the volume, no? Both terms. And therefore, here we can say that the derivative of P with respect to temperature is Q divided by T. And instead of N2, we can put P divided by KBT. So this is P divided by KB. And here I have a T squared. Okay, tutti quadro. Okay. Now it's just a matter of solving this equation. So I have that dP divided by pressure is equal to dt, well, q divided by kb, yeah, but dt divided by t squared. Now we have to integrate among between, let's say, state A and state B. And at the end, we will have here, we have the log of PB divided by PA. If we integrate from 2 points that we call A and B. And here we will have a minus K divided by KB. And here we have temperature, again, between A and B, which is equal to Q divided by KB. And here, yeah, 1 divided by TA, and 1 divided by TB, which is equal to K divided by KB, TB minus TA, TB. Q by KB, va bene, correct. So, and finally we get the following result, that PB is equal to PA times the exponential of Q divided by KB, TB minus TA divided by TB. Okay. Of course, now TA is a fixed, TA and PA is fixed, and what is the equation is telling me is that if I have here, so we have P and T, this PA and this PA, we have as a function of B, we have an exponential. So to good approximation, the first order phase transition line between liquid and gas is an exponential. And A. Whereas one can find that in the case of solid, liquid solid, the line is much smoother in the sense that the slope is much smaller. But in the case of the liquid gas, due to the change, due to the difference between the densities, actually the shape is almost an exponential shape. And I would say that we stop for 5 minutes because I guess we are a little bit tired. But we cannot do much more than staying here. Now let's try to make a small exercise out of this and how to apply this equation. So now let's apply this equation to the case really of water and vapor, for which I have some numbers. Okay. So let's consider water, vapor. For which we have the latent heat per gram is provided by, is given by this number here, is 2,072 is joule per gram. But in here we have latent heat per particle, so we have to do a small correction, a small modification of this. So the latent heat per mole should be equal to this number here, 2272 joule per gram, times this H2O is more or less 18 grams per mole. And from this I get 40,896 is joule per mole. So that means that when you have the transition from water to vapor, this is the latent heat per mole associated to this phase transition, and this number here will allow, for instance, to establish once you change the condition of your system in a mixed phase. To study, for instance, how does one phase, if you change the temperature, as we will see in a moment, how much phase is in the condensed phase or in the vapor phase, so in the liquid phase or in the gas phase. Okay, just a matter of making two more calculations. So in the exponential that we had before, we have Q divided by KB. This can be, is the heat, is the latent heat actually, is latent heat per particle, N. And now the N, so this is latent heat divided by KB times NA, Avogadro number, times N, where this N is the number of moles. Okay? And therefore now this, for 1 mole, for N equal 1, we have that Q divided by KB is the latent heat per mole that we have determined before, divided by KB and A is just R, is the constant, universal constant of gas, no? And now this, for N equal 1, this number is 49, what I have here? What number is this? 19 Kelvin. 4919 Kelvin. Okay, so then for water, can write the following equation, which is the first order liquid gas phase transition line, which will be the following: P of T. Now I have to put here a value of the pressure of the state A. Suppose that is 1 atmosphere. And here we have exponential of this Q divided by N, which was provided by this number here. So 4919 Kelvin. And here I have a T minus, and here I have T. Here you have to put the temperature of phase A, and TA in this case is equal to 373 Kelvin, which is the boiling temperature for P equal to 1 atmosphere. Okay, is 100 Celsius. Okay, so then here we have 373, and here we have 373. And then we can close it. Okay, so now this line, so this function here with those numbers describes the first order phase transition line for water vapor, for the water vapor phase transition. Okay. Now suppose that we want to do this little exercise. You have 1 mole at T equal to 373, so exactly at the boiling point at 1 atmosphere, and cool down at fixed volume down to 336 Kelvin. So you decrease the temperature by this amount. So the final temperature will be 336. Which fraction of vapor has passed to the liquid phase? Okay, so this is the question. Now, to do that, we just need to now basically solve this equation, no? Well, in principle, let me write this in a little different way. Forse questo lo possiamo cancellare. Questo lo cancello un attimo. So let's say that the equation of before was the P in the final state is a P which is computed for 336 Kelvin, and the P in the initial state is the P computed at 373 Kelvin, and this must be equal to the exponential of Q divided by N, which was 4919 Kelvin, times, here you have a delta T divided by T initial times T final. Okay, and delta T is equal to 336 minus 373 Kelvin. T initial and T final, T initial is 373, T final is 336 Kelvin. Okay. Now, if you put those numbers in here, you get the ratio between pressures is equal to this number that I'm going to write. So you insert those numbers here, and then you get that this is almost equal to 0.23. So this is the ratio of the pressure, in the final state and the initial state. Okay. Now we know, again, from the ideal gas equation of state, that PV is equal to KB M F TF, where F is final. And again, B initial is equal to KB and initial T initial. I can get from here that the ratio of PF divided by PE PI, sorry. So maybe let's write this PI is better. TF initial is fine. And PF divided, since the volume is constant, is equal to NF divided by NI, and then I have TF divided by TI. And from these you can get that NF divided by NI is equal to PF PI times TI divided by TF. Now you put the numbers. So PF divided by PI is 0.23. And you put also the ratio between the temperature, and finally you get 0.26. Okay? Which means that the 74% has formed water. So this is the fraction of gas in the final state, and the complementary, so 74% as condensed into water. Okay. So by knowing the latent heat, well, you can compute this kind of, you can make this kind of exercise, no? So to change the state of the system and see how much phase you have in phase one, or how much particles you have in phase one, and how many particles in phase two. So to close the session, the section of first order phase transition and thermodynamics. So from the next time we will deal with, we will start with statistical mechanics. I want to present you another result of thermodynamics, which is remarkable, which is the Gibbs phase rule, or phase transition for multi-component systems. So phase transitions for multi-component systems. Subtitles is Gibbs phase rule. Now, This base rule, as you will see, it's a very simple rule that determines how many parameters you need to describe your system, your multi-component system, or how many, well, it determines basically what could be the structure of the phase diagram. How many, if you can have a tripole point, how many phases you can have at equilibrium, and so on and so forth. So let's do the following. It's basically a part of computation of independent variables and known quantities. So suppose that you have n components, which means n different chemical types of matter, chemically different types of matter, and suppose that we have r phases. A phase, so different phase of the same matter just means that the chemical composition is the same, just that they are in a different phase, liquid, gas, solid, etc. Now, for what we said before, when you have equilibrium, so chemical equilibrium, thermodynamical equilibrium, the phases must be in thermal, mechanical, and chemical equilibrium. Which means that the temperature, the pressure must be the same, and also the chemical potentials of the different phases and of the different chemical components must be equal. Okay? So actually, this last sentence, chemical equilibrium, needs, well, means many equations. How many equations? Suppose that we indicate with mu J I the chemical potential, where J determines the phase, is the phase index, whereas I is the chemical index. So mu1 means phase 1 of the chemical substance 1, and so on and so forth. Okay. So J runs from 1 to R, whereas I runs from 1 to N, to N components. Okay, so let's try to write down the equations of chemical equilibrium in the mixed phase. Sono 36, no, 70. Chemical equilibrium means mu1, which is the chemical potential of, in phase 1 of the chemical component 1, is equal to mu1 of phase 2, blah, 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 mu1, up to which number? Well, R runs, the index, the upper index runs from 1 to R. So you have mu1 of R. Okay. So this is the same chemical component, and those are the different phases. Suppose that here we are not considering a mixed phase of two components, but of n components, and in principle we can have r different phases in equilibrium. For water, the maximum you can have is just 3. You can have a tripole point, but in general this could be larger. So then you write down all the equations like that. Mu2 1 is equal to mu2 2 blah 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 up to mu2 r up to the n component chemical component and this mu and R. So those are the chemical equilibrium equations. How many equations we have here? Well, I have n times each of these lines contain r minus 1 equations. So it's n times r minus 1. Okay. So those are the equations that we can use in order to reduce the number of free independent variables. And it does introduce not the number of independent variables. And let's do the following. So suppose that we introduce this quantity xik is equal to nik divided by the sum over from I1 to n of nik. So what is nik? Is the number of particles which are in phase K for the component, for the chemical component I. Okay, so the lower index is for chemical component, the upper index is for the phase. And therefore, these xi are basically the concentrations. No? So because you take the number of particles in phase K of the, let's say, E of the I chemical component, and you sum over I. So this is the ratio in the same phase, in the phase K, of the number of particles I with respect to the total number of particles. So those are, let's say, concentrations. So it could be the number of particles of salt with respect to the total number of particles in a solution of salt and water, for instance. Now, of course, we have a normalization conditions, which is the following, that if you sum from I to n, of xik must be equal to 1. Okay? This trigger it from this equation. Now if you sum x over I, then you need 1. That means for each single phase, for each phase, the number of concentrations which are independent is n minus 1. I have n minus 1 number of concentration. Okay, just instead of let's say considering the number of particles of each species, I just consider concentrations, and then since I have to normalize with respect to 1, I just have n minus 1 independent concentrations, whereas I would have n different number of particles, of course, for each phase. So that means that the number of independent variables, since this is for each phase, is r times n minus 1. So in total, I need to specify the condition of the system. I need n minus 1 times r concentrations. Okay, So for each phase, I need n minus 1, therefore in total, I have n minus 1 times r, number of independent concentrations. So we can now consider the total number of parameters that are needed to characterize the system, which is, let's call it NP. So this is the total number of parameters needed to specify the conditions of the system. Well, of course, these are independent parameters or independent variables. So we have a system in which we have r possible phases and n possible and n chemical different components, which is the number of independent parameters or independent variables that we need to completely specify the state of the system. Well, this number NP is provided by the following counting. So NP is equal to 1 plus 1, 1 for temperature, 1 for pressure, because in the mixed phase, temperature and pressures are equal in the different phases, plus I need this n minus 1 R concentrations, times R different concentration. For each phase, I have n minus 1 independent concentrations, but I have also some constraints, n minus 1, which is, so this is the number of independent concentrations, minus, I have this n R minus 1 equations of chemical equilibrium. Okay, so the total independent number of parameters is provided by these equations, which at the end provides the following number. It's 2 minus plus 1 minus r. Okay, and r goes away. So it's 2 plus n minus r. Okay. Now this is called Gibbs phase rule. And it has several interesting applications, which, for instance, one is the following. Since NP must be larger, equal than 0, then that means that R must be smaller than 2 plus n. Smaller equal 2 plus n. Okay, so that means that this is the maximum. So R equal to 2 plus n is the maximum number of phases in coexistence. Selection existence. Okay. So these are the two interesting things: the number of independent variables and the total number of phases which can be in equidistance. So let's take some example. Suppose that n is equal to 1, so one chemical component, which should be water, for instance, H2O, which is the maximum value of phases, is 3. 3 number of phases in existence. What is this 3 number of phases in existence? For what is the triple point? Okay. Now, for the triple point, you see also that since let me see, this is n1 and this is r is equal to 3. So for the triple point, np is equal to 0. Okay, because this one, this is 3, and is np 0 by definition of the maximum number of phases, which means that no independent variables. Indeed, it's just one point, no? The triple point is already in the name, it's a point in the phase diagram. So it's just one point, I cannot change pressure, temperature, and nothing. Okay, it's just one point. Now, these rules determines also the number of independent variables for a single phase or for a mixture of 2 phases or 3 phases, or how many phases I want. Indeed, the applications are several. It's a very, very nice rule. So suppose that I have r equal 1, so just one phase. So if r is equal 1 and n is equal to 1, I get np is equal to 2. So which is the number of independent variables that I need to specify a single component phase. One phase, one component is np equal to. Which are these 2 independent variables? Well, they are the pressure and temperature. They are independent. Okay? And indeed, in the phase diagram, let's make the usual water phase diagram. If I am, for instance, in the solid phase, in the solid ice, well, for the single phase, one component, each of these points is specified by 2 numbers, which is the pressure and the temperature. Pressure and temperature. Then we have this point, which is the triple point, that is in this condition, 3 phases in equilibrium. Okay. And suppose now that I have r equal to 2. So 2 phases, one component. One component, I mean chemical component, okay? And 2 different phases. Now I just need to put those numbers in here, and that I get that this is n equal, this np equal to 1. So just one independent variable, and this is correct, because if I consider the coexistence of 2 phases, For instance, let's take the liquid gas. And this is the line of coexistence. And if I determine if I fix the temperature, the pressure is automatically determined. Okay, so I'm moving along this line, so I just have one independent variable, which is the temperature or the pressure, and one of the two can be determined from the other one. And equal 1. Now the situation gets complicated when considering the number of chemical components. So this is just water, n equal 1, for instance, is water. Now, if the number of components is larger, then the situation can be as messy as you want. The phase diagram, now they are can be really complicated, and only Russians can deal with them when you have many components. So suppose, for instance, that we have n equal to 2, so two different chemical components, which is, for instance, the case of a solution of water and salt, for instance. This is just an example. Now, for n equal to 2, the maximum number of phases in equilibrium. So let me write down again the equation. N is equal to 2 plus n minus r is 4. No? This is it's not a triple point, this is a quadruple point. Quadruple, I'm not really sure it's quadruple. Okay, so I have one point in which 4 phases now coexist and not 3 as in the case of water. And we can, of course, move on and try to make the computation for other phases. For instance, R equal 1, so 1 phase, and we have fixed n equal to 2. In this case, Np is equal to 3, which means, for instance, pressure, temperature, and one concentration of salt, for instance. Okay. 3 independent variables. Suppose that instead now we consider again 2 components, chemical components, and 2 phases. So R equal to 2 and N equal to 2. That means that the number of parameters is 2 for describing the coexistence of 2 phases. Now you need 2 parameters. That is different for the case of water, in which you just need 1. If you know the temperature, you just know the vapor pressure automatically. Whereas in this case, if you know the temperature, you also need to specify another parameter, which could be the pressure, or could be the concentration of one of the components. Indeed, for instance, let's take again a solution. For a solution, we need, for instance, temperature and concentrations of salt. We are talking about water and salt. That means also that the pressure of the phase transition or if you want the line of the phase transition, depends on the concentration of salt. It's not a line anymore; it's a surface in the phase diagram. The pressure of this depends on the concentration of salt. Okay. And indeed, you know that whereas in the case of just water, the cryogenic point is the point of the boiling points are at 0 and 100 respectively, no, for water. So 100 Celsius is the boiling point, and 0 at 1 atmosphere is the freezing point. Or fusion, depends on which direction you are looking at. But for water plus salt, for instance, it's not like that anymore. The temperature of fusion or freezing and the temperature of boiling or condensation depends on the concentration of the other component of the system. No? And of course, you can have, well, actually, we know, in fact, that there is a cryoscopic lowering. So the temperature of freezing or fusion is smaller when you are in presence of a solvent. Okay, and you have also a bulioscopic. I found this recently, it should be corrected. No? Bulioscopic elevation. Abbassamento cryoscopico e innalzamento bulioscopico. Avete sentito, no? Okay. So it depends on the fact that you have different, so the temperature or the pressure at which you have the phase transition depends on the chemical component, well, on the amount of, for instance, salt that you have in your solution. Okay, it's not something that is fixed anymore. Well, it's one. I think this is done. So next time, which is Thursday, we will move on and we'll start with something which is more into the statistical approach to those macroscopic systems. So the thermodynamical reminder is finished. Arrivederci.
Arrivederci.